So student, today we are going to start the new topic as an oscillation. So previously already you have studied the different types of motion. So in that different types of motion, the first type of motion we have seen as a straight line motion, or this straight line motion is also called as a rectilinear motion. Rectilinear motion means what? Whenever your particle is moving from A point to B point along a straight line, and this motion will take place in a rectangular plane formed by x bar axis, then such type of motion is to be called as your rectilinear motion. Then also in previous standard, 11th standard, you have seen circular motion. That is when particle is performing motion along a circumference, either clockwise or anti-clockwise. That type of motion is to be called as your circular motion. Then, in your 12th standard first chapter, you have seen one more type of motion, which is called as rotational motion. In that, your particle is performing a rotational motion about an axis with a constant angular velocity. So these three types of motion already you have seen. What is first one? Straight line motion or rectilinear motion, in which particle is traveling along a straight line. This is the first type of motion. Second type of motion you have seen when the particle is performing a circular motion along a circumference of a circle. It's called circular motion. And third we have seen when particle is rotating about axis of rotation with constant angular velocity. Such type of motion is to be called as a rotational motion. Is it right? And now in this chapter, as an oscillation, we are going to study the fourth type of motion, which is to be called as a oscillatory motion. Now, what is oscillatory motion? We can take one simple example. Let's consider the sun is located in the planetary system, and around this sun, Earth is rotating in an orbit, and around the sun, Earth will complete its one rotation in time interval t is equal to 365 days. So, Earth will take time interval as 365 days to complete one rotation. If she want to begin another rotation, at that time, again Earth will take 365 days. Means after each 365 days, the motion of Earth around the sun will get repeated. So this is nothing but the repeated type of motion which will occur periodically. So this motion I am going to call it as a periodic motion. Another example we can consider as a Earth is rotating around itself. The Earth will rotate around itself, and for Earth rotation around itself, it will take a time interval as a 24 hours. So after each time, which is equal to 24 hours, Earth will do the repetition of the motion. So some type of motion will be exist in the nature where these motion will get repeated after equal interval of a time. So in the nature, there are some type of motion which will get repeated after a fixed interval of a time. That type of motions are to be called as a periodic motion. And the cycle of that motion will repeat again and again. So this is to be called as a repeatedly periodic motion. Okay, now I consider give the one more example. If I am saying that the motion of a pendulum, let's consider this is the pendulum. To this pendulum, if I apply a force, then this pendulum will start oscillating about the mean position. So this motion of an pendulum start its motion from O point. It will goes to A. From A again it comes to O. From O point it will go to another position as a B. And from B again it comes to O. So like that manner, the pendulum continuously oscillates in between A point to B point. So in this type of motion, the pendulum is moving to and fro. To means in the forward direction and fro means in the backward direction. So the pendulum will oscillate to and fro. And this motion will get repeated after certain fixed interval of a time. That type of motion is to be called as your oscillatory motion. So in this oscillatory motion, the three things are going to be happening. One is motion is repeated. That repeated motion will occur after fixed interval of a time. And the third thing is the particle is moving to and fro. That type of motion is to be called as your oscillatory motion. Now in this oscillatory motion, now what is going to be happening? That is in oscillatory motion, your particle is moving to and fro. So let's consider O is the mean position and particle is moving in the forward direction. Like this in example, in the forward direction, that is at point A. So particle is moving in the forward direction, means the particle is moving to, and this motion will go to the another same position as a B also. The particle first will move from O to A, it will come back to A to O, then O to B and B to O. So this type of motion, which is a to and fro motion, which will occur after fixed interval of a time along a straight line. So this type of motion is to be called as your oscillatory motion. Now this oscillatory motion, for that oscillatory motion, I can calculate the displacement of that particle. I can calculate the velocity of that particle while performing the oscillatory motion. As well as I can able to find out the acceleration also. But all these three physical quantities, displacement, velocity and acceleration, are the sine or cosine function of time. Means your displacement, velocity and acceleration can be expressed in terms of sine or cosine function. And therefore, this type of motion is to be called as a harmonic motion. Because in oscillatory motion, their displacement, velocity, acceleration are the sine and cosine time dependent function. That's why that oscillatory motion is to be called as a harmonic motion. Now harmonic motion means I can say it is a simple harmonic motion. So this simple harmonic motion, why the word is used harmonic? Because displacement, velocity and acceleration are expressed in terms of sine, cosine and time function. That's why it is to be called as a harmonic function. Now these harmonic function, I can call it as a simple harmonic motion. In shortcut, I can underline the first letter from simple, first letter from harmonic, first letter from motion. And if I collect that term, I am getting SHM. this is to be called as a SHM motion. This SHM motion are of two types. One is linear SHM and the second one is angular SHM. So this linear SHM and angular SHM will be nothing but two types. So two types of SHM, linear SHM and angular SHM. In that linear SHM, particle is moving to and fro along this straight line. While in angular SHM, particle is moving along an arc of a circle. That's why it is to be called as a angular SHM. So now we are going to concentrate more in detailed manner as a linear. Clear? So for that linear SHM, I can concentrate a very simple example. So now I am going to concentrate on linear SHM. In that linear SHM, I can concentrate here one spring whose one end is attached to rigid support. Another end is connected to one block of mass m and it is provided with some hook initially. Now, for this block, if I will apply a force away from the rigid support, if I apply a force on this block, here no force is applied, so I can say that applied force is equal to 0. But if I apply a force on a block away from the rigid support, so what you will get is that the picture of your spring, the spring you will get it in the form of extended form. Means now your spring will get extended. How much is the extension? See that this is the initial position, I can see. From that your block get displaced. The motion of block will get displaced. Means now displacement will occur here of the spring. But due to property of elasticity, a restoring force is acting on the spring whose direction is towards the rigid support. That is due to property of elasticity, spring wants to regain its original size and shape. So on this spring, two forces are acting. One is applied force, which is away from the rigid support. Due to that, spring will get extended to a certain displacement x. But due to property of elasticity, spring wants to restore its original position. So that force is called as a restoring force. Means your applied force and your restoring force, their directions are opposite. Restoring force and displacement, they are in the opposite direction. Restoring force direction is towards rigid support. Displacement direction is away from the rigid support. Means what I can say that the restoring force is directly proportional to displacement with negative sign. Negative sign indicates that the direction of restoring force and direction of displacement of the springs are opposite. But if I apply more applied force, spring will get extended more. Spring extension is more. Restoring force is also. So in magnitude wise, restoring force is directly proportional to displacement. But their directions are opposite. Fine. Suppose now if that same spring is compressed. Compressed means what? I'm applying applied force towards the rigid support. So this spring will get compressed. Spring will get compressed means now spring get compressed through a certain distance x. Now the displacement during compression is towards the rigid support. But Due to property of elasticity, spring want to come back to the original position. So your restoring force will be away from the rigid support and applied force will be towards the rigid. Due to applied force, spring is compressed. Your displacement x means displacement x is towards the left hand side. Restoring force actually is towards the right hand side. So the direction of restoring force and displacements are opposite, but they are proportional to each other. If I apply more force in the compression, spring get more compressed. So displacement of compression is also, so in magnitude wise, restoring force and displacement, they are directly proportional to each other, but their directions are opposite. Clear? Okay, fine. Suppose now, in the first example, I have applied force away from the rigid support, the spring gets extended. If I extend that spring in the large strength, and if I release that spring, what happens? Spring will start oscillating to and fro. Spring will move backward, forward, backward, forward. So that type of motion is to be called as your linear simple harmonic motion or linear SHM. So in the linear SHM, when applied force, the spring will get extended, and if I release, so the spring has a tendency to go back to mean position, but it will not relax at mean position. It will get again compressed due to inertia. Means when it will go to mean position, its velocity will become maximum. That's why it will go to the compressed state. When it will reach to compressed state, its velocity will become again zero. So it will again come back to the position. So in that manner, there will be a position of that spring will get changed continuously along a straight line. That is the linear SHM. So now, in this linear SHM, from the diagram, what I am getting here, that is restoring force is directly proportional to displacement, and negative sign indicate that their directions are opposite. In this, I will take one more example. If you are considering a U-tube, in that U-tube, if I fill the liquid, so this liquid level in the U-tube are initially at the same level, but to the other open end, if I apply a balloon, if I apply the balloon, so and to that balloon, if I apply a certain force, if I apply a force, so if I apply a force, means here on this liquid column a pressure is created. If pressure is created in the another U arm, the liquid level rises. And if I release the force, now if I release the force, so if I release the force, this liquid level will dance up and down along a straight line. Liquid level will bounce up and down along a straight line. So this is also the example of linear. Another one, you are knowing that if you are taking a hydrometer, so your dropper by which you are filling the ink, if you take a hydrometer, that hydrometer shape will be in this format. Here is the balloon. And with that hydrometer, I will insert inside a liquid level. So when no force is applied, that hydrometer will bounce. If I apply a force on this hydrometer, so that liquid gets inserted, and if I release that, then that hydrometer will bounce up and down inside the water bubble. So this is also your example of linear simple harmonic motion. So now, while writing the definition of linear simple harmonic motion, You have to remember three things. Meaning of linear. Linear means particle is performing a motion along a straight line to and fro, so that a restoring force acting on the particle is directly proportional to the displacement. But direction of force and displacements are opposite. Such type of motions are to be called as a linear simple harmonic motion. Clear? Now, here I will get one more definition. What I say that force F directly proportional to minus x. If I remove this proportionality sign, I can add a proportionality constant as a k. So F is equal to minus kx. While according to your Newton's second law, we are knowing that force is equal to mass into acceleration. So instead of F, I put mass into acceleration is equal to minus kx. Therefore, acceleration is equal to minus k upon m into, where k is force constant, mass is constant. Means what in short I write, acceleration is directly proportional to mass. So that will also give us a definition of linear. How this is it. Linear simple harmonic motion is a motion of an particle when particle is moving to and fro along a straight line. At that time, acceleration acting on a particle is directly proportional to the displacement and their directions are opposite. Or you can say that the particle motion is always towards the direction. So in that manner, you can define linear SHM. So in that linear SHM, these 3 points are important. Straight line motion, to and fro motion, and in that force is directly proportional to displacement, but their directions are opposite. Clear? And now we are going to switch over our first question, and that first question is nothing but derive differential equation for linear simple harmonic motion. Now, how we can start? From the definition of linear simple harmonic motion. According to definition of linear simple harmonic motion, it is very simple, just remember very carefully. According to definition of linear simple harmonic motion, F is directly proportional to minus x. Hence, I can write down F is equal to minus kx. K is a force constant. That is equation number 1. Clear? Then, according to Newton's second law, force is equal to mass into acceleration. That is equation number 2. If you concentrate on equation 1 and 2, the left hand side gives the force. Therefore, the right hand side must be same. So, from equation 1 and 2, what I write? Mass into acceleration is equal to minus kx. Means I can write down acceleration is equal to minus k by m into. Is it okay? Now, acceleration. Acceleration can be written as dv by dt, which is equal to minus k by m into. So instead of k as acceleration, I have written this formula. Acceleration is defined as rate of change of velocity with respect to time. Then d dt of, I can write definition of velocity. Definition of velocity is dx by dt, which is equal to minus k by m into x. So this I can write down d square x by dt square is equal to minus k by m into x. Instead of this k by m, I can put a constant d square x by dt square is equal to minus omega square x. Means for k by m, we have assumed substitution as a omega square. So I can rearrange now this equation. And in rearranging the equation, what I'll write down here? I will write down that equation as a, okay, I'll write here d square x by dt square plus omega square x is equal to, and this is to be called as your differential equation of an simple. Finish your 2-mark question. Is it okay? So see that first step. From definition, F is equal to minus kx, equation number 1. From Newton's law of Coulomb, F is equal to mass into acceleration, equation number 2. Half mark here, half mark here. Equate them, so you will get acceleration. Use the definition of acceleration in terms of velocity. Use the definition of velocity in terms of change in displacement per unit. So you will get this d square x by dt square is equal to minus omega square x. This minus term, if I shift to the left hand side, the term will become plus, and I will get the equation. So this is your simple 2-mark question. Clear? Now, here one more question is there. That is, derive expression for period of linear SHM. So the next thing I can say, period of linear SHM. Have you got the shortcut? L for linear, SHM for simple information. I want a period. Period means capital T. So this capital T now you want. So now, what I use here? We know that. What we know that? Omega square is equal to k by m. Therefore, omega, which is equal to under root of k upon m. Omega is nothing but 2 pi upon t, which is equal to under root of k by m. This omega is equal to 2 pi t. This formula we have seen circular motion. Therefore, now what I can say that, therefore t by m, 2 pi, taking inverse of both sides, because I want expression for period. So t factor should come to the numerator, taking inverse. It is equal to under root of m by t. Therefore, t is equal to 2 pi under root of m by t. This is nothing but your formula for period of linear. If it is period, then I can write for frequency. Frequency is equal to reciprocal of period, that is 1 by 2, which can be written as reciprocal of this equation, 1 upon 2 pi under root of k by m. So this is nothing but your formula for frequency of. Are you getting any doubt? Clear? So now, whatever portion till now I have covered, there are 2 questions. First question is derive expression for differential equation of SHM, and the second question is what is the period and frequency of a linear SHM. Is it right? So today we have completed up till now, and the next lecture we can go for the next one. Fine? Is it okay? Any doubt? Clear? Here, now you are knowing the differential equation. In that differential equation, so your differential equation, I can say differential equation of linear SHM. d square x by dt square plus omega square x is equal to 0. This is the differential equation. Now your 3-mark question is there. That 3-mark question is derive acceleration, velocity and displacement of linear simple harmonic motion. There is 40 marks. Each part carries 1 mark. Okay, so we have to start from differential equation. So what is our first step? Differential equation of linear SHM is, first you have to write differential equation. From differential equation, what I write? D square x by dt square is equal to minus omega square. D square x by dt square, differentiation of x 2 times means that is nothing but your acceleration. So acceleration is equal to omega square. So now I am getting first formula for acceleration. When particle is performing linear simple harmonic motion. So when particle is performing linear simple harmonic motion, your acceleration is equal to minus omega square. Clear? Now, once you got the acceleration, so I will say that, I will write down here as it, acceleration, that is d square x by dt square, which is equal to minus omega square x, which is nothing but the acceleration. Now from acceleration, now I will go for the velocity. That is derivation for velocity. How you can find the velocity? Start from acceleration. Acceleration is, I can write acceleration as a, acceleration can be also written as dv by dt, which is equal to what value we are getting for acceleration? Minus omega square. I will rearrange this term, dv by dt. Instead of dv by dt, I can write down dv by dx multiplied by dx by dt, which is equal to minus omega square x. Dx will get cancelled. You will get your original term, dv by dt. So what I say now? Dx by dt. This dx by dt is nothing but your velocity. This is what I write down here. dv by dx into v is equal to minus omega square x. Clear? Therefore, I can write down v dv is equal to minus omega square x dx. This dx term I have shifted. Clear? Now from v dv, I want only velocity. So dv is here. Differentiation of v with respect to dv means I have to now to find out v, I have to do the integration. So by integration, so I'll take integration. Integration of v dv is equal to integration of minus omega square x. Integration rule. V dx, variable is v, power is 1. So in integration, the power of variable is increased by 1 divided by total power. Now here originally power is 1. So power will be increased by 1, means 1 will increase by 1, means it will become v square. Divided by power, power is 2, is equal to minus omega square, which is constant. Integration of what? X dx. Again now variable is what? X. Its power is 1. So integration of x dx, power will rise by 1. Means 1 power will rise to 2. So it will become x square by 2 plus integration. And now I have to calculate the value of integration constant. How I can calculate the integration constant? For that, if I am saying that displacement of the particle is 0, if the displacement of the particle is 0, then particle will be at mean position. And when particle is at mean position, At that time, its velocity is 0. But when your particle will reach to extreme position means it reaches to its amplitude. That is when x will become plus minus a. At that time, you will get the velocity. Is it right? Means at that time when particle reaches to extreme position, it will not remain at extreme, but it again start coming back. Means when it reaches to extreme position, its velocity will become 0. So if I put these both the values in the upper equation, what I am getting 0 is equal to minus omega square a square upon 2 plus, means I am getting value of c. I can put here. I will get value of c is omega square a square by 2. This I am getting as a value of c. That value of c I can substitute in the equation of v square. So now my equation will become, so this equation will become, I can write down v square by 2. See this first term is equal to minus omega square x square upon 2 plus c. Value of c is what? Omega square a square by 2. Two factor occurs in left side, right hand side. So two factor will get cancelled. So what I am getting, v square is equal to minus omega square x square plus omega square a. In the right hand side, omega square common term. Omega square. First term will come minus. Instead of minus, I will take first positive term. So a square minus x. Taking square root of both sides, so what I am getting, v is equal to omega under root of a square minus x. And this is nothing but your velocity when particle is performing linear. And here is your acceleration when particle is performing linear. Okay? So this is about your acceleration and you go through this video 2-3 times so that you come to know that. Clear?